All right, everyone, grab a seat and let's get settled. I am absolutely thrilled to have you here for today's masterclass on reaction energy. If you're a chemistry student gearing up for exams, you are in exactly the right place. Today, we're going to completely demystify one of the most foundational concepts in all of chemistry, and that's how energy moves during a reaction. We're going to break down the invisible forces that make reactions hot or cold. And honestly, by the end of this explainer, I guarantee you'll be looking at the everyday world around you completely differently.
So, I want to kick things off by having you think about a really simple question. Why is it that when you light a candle, it pushes heat out into the room and warms your hands, but when you hold an ice cube, it actually steals the heat from your hand to melt, right? In both cases, a physical change is happening, but the flow of energy is moving in completely opposite directions. Why does nature do that? Well, the answer lies in the incredible mechanics of reaction energy.
Okay, let's dive into this. Here is our roadmap for today. 1. Heat in versus heat out. 2. Bond breaking and making. 3. Real-world chemistry. 4. Energy level diagrams. And finally, 5. The exam cheat code. Let's get right into it.
Section 1. Heat in versus heat out. Decoding the Greek roots.
So, our absolute first step is mastering the vocabulary. Now, I know chemistry terms can sound incredibly intimidating, but here's the secret. They're almost always just simple descriptions hiding in ancient Greek. If you can decode the words, you instantly know how the chemistry works. Let's look at our 2 stars for today, exothermic and endothermic. The prefix exo means external, or outside. Think of everyday words like exit or exoskeleton. Thermic, as you probably guessed, means heat. Put them together, and exothermic literally translates to external heat. These are reactions that release heat energy out to their surroundings, kind of like our burning candle. On the flip side, endo means internal or inside, so endothermic means internal heat. These are processes that absorb heat energy from their surroundings, taking it inside themselves to drive a change. Exactly like that melting ice cube stealing heat from your hand. Burn these root words into your memory, and I promise you, you will never mix up the definitions on a test.
Moving on to Section 2. Bond breaking and making. The atomic level.
All right, let's zoom away from everyday objects down to the microscopic level. What is actually happening to the atoms to cause these massive energy shifts? Well, I always like to teach this by looking at isolated atoms. Picture 2 single hydrogen atoms floating around. On their own, they're super highly energetic. They've just got all this excess energy. But nature is kind of lazy. It prefers stability. So when those 2 hydrogen atoms finally come together and make a bond to form an H2 molecule, they drop down to a much lower relaxed energy state. But where does that extra energy go? It has to go somewhere, right? It gets released to the surroundings. Let's say they lose 2 joules of heat energy. Because heat is released, bond making is always an exothermic process, period. Conversely, if you want to break that H2 molecule back apart, you have to force energy into it. It has to absorb those 2 joules from the surroundings just to snap the bond. So bond breaking is always an endothermic process. Making bonds releases energy, breaking bonds requires energy.
Section 3. Real-world chemistry. Processes. Okay, so we understand the atoms, but chemistry isn't just about isolated hydrogen. It's about the entire world around us. And in an exam setting, you are absolutely going to be tested on your ability to recognize practical, real-world examples. So I want you to take a mental screenshot of this list right now, because these are your high-yield exam examples. For exothermic reactions, our heat releasers, we've got combustion, which is just burning fuels. We've got cellular respiration, which is the process keeping you alive literally right now. We also have rusting iron and physical processes where things come closer together, like condensation forming clouds or water freezing into ice. Those all release heat out. For endothermic reactions, the heat absorbers, we've got photosynthesis, where plants literally absorb sunlight. We have melting ice, evaporating water, splitting gases apart, and certain specific chemical mixtures, like combining water with ammonium nitrate. Again, lock this list in, it's super important.
Section 4. Energy level diagrams. Graphing the invisible.
Now in chemistry, we don't just talk about energy changes. We have to actually map these invisible shifts onto a graph. Think about how this works for an exothermic reaction. The reactants start way up high on the energy scale, but the resulting products end up way down low. Because the products have less energy than the reactants, that difference in energy had to exit the system, right? It essentially fell off a cliff, and that lost energy was released into the surrounding environment as heat.
And this brings us to a vital term for your class, enthalpy change, which we represent with the symbol delta H. Enthalpy change is just a fancy way of describing the mathematical difference in energy between the products and the reactants. Think back to that graph we just talked about. Because an exothermic reaction drops from a high energy state to a low energy state, the mathematical difference is negative. So here is an incredibly important rule for your exams. Delta H is always negative for exothermic reactions. And, as you'll see in a second, it's always positive for endothermic reactions.
Speaking of those endothermic reactions, let's think about their graph. It is the exact opposite. The reactants start down low and the products end up high. Imagine trying to push a giant boulder up a steep hill. You literally have to pump energy into it. These reactants must absorb energy from their surroundings just to climb up to that higher energy state. And because the final energy is higher than the starting energy, the enthalpy change, our delta H, is a positive number.
Section 5, the exam cheat code, calculating reaction types.
All right, class, we have reached my absolute favorite part of today's masterclass. You understand the concepts, you know the graphs, but what happens when you're sitting in an exam, the clock is ticking, and you are staring at some monstrous chemical equation you've never seen before in your life? You need a cheat code. So here is a super simple 4-step formula to find a value we are going to call N. Step 1, count the total number of moles on the product side of the equation. That's the right side. Step 2, count the total moles on the reactant side, the left side. Step 3, subtract the reactants from the products. So N equals products minus reactants. Step 4 is the magic key. If your final N value is greater than 0, boom, it's an endothermic reaction. If N is smaller than or equal to 0, it's an exothermic reaction. It really is that simple. Let's test it out together.
Okay, here's your first practice question. Imagine you're looking at an equation on your test. You count 4 moles of reactants on the left, and you count 2 moles of products on the right. Is it exothermic or endothermic? Do the mental math right now using our formula, products minus reactants.
Let's see if you got it. Products minus reactants means 2 minus 4, which gives us an N value of -2. Since -2 is less than 0, we instantly know this is an exothermic reaction. Man, it's incredibly fast, isn't it? Let's throw a slight curveball to test your conceptual memory from earlier. What type of reaction is the splitting of methane gas into carbon and hydrogen? Think about the physical action happening here. You have a gas molecule, and you're splitting it apart. What did we learn about breaking bonds? Exactly! It's endothermic. Remember, just like breaking that tiny H2 molecule apart at the atomic level, splitting a gas molecule always requires absorbing energy from the surroundings. You have to physically force energy in to snap those chemical bonds.
Let's do one final classic exam scenario. Seriously, this one shows up all the time. Silver bromide decomposes into silver and bromine gas when it is exposed to sunlight. Fun fact, this is actually the exact chemical reaction that made old-school photographic film work. So is this exothermic or endothermic? Really think about the role of the sunlight here. It is endothermic. The total giveaway phrase there is exposed to sunlight. The light is the energy. The silver bromide is physically absorbing light energy from its surroundings to force a decomposition reaction. Because it's actively pulling energy in, it fits the absolute perfect definition of an endothermic, or internal heat process.
Now, as much as I love that moles of products minus reactants trick we just learned, I do want to leave you with a very direct warning from our source material. To quote them directly, remember that this trick has some exceptional cases. Just be careful while using this trick too often. The math trick is a fantastic tool to check your work, or to take a solid guess when you're completely stuck. But it definitely has exceptions in advanced chemistry. Don't let the cheat code replace true understanding. Think about the bonds breaking, think about the energy flowing, and think about whether the system is absorbing or releasing heat. If you master the core concepts we covered today, honestly, you won't even need to rely on tricks. But it does leave us with one final thought, class. If life itself, from the burning of giant stars to the firing of tiny neurons in your brain, is just an endless chain of endothermic and exothermic reactions, what does that say about the energy you were putting out into the world today? Keep asking why, and I'll see you in the next masterclass.